Okay, good morning, everyone. We are pleased to have Renbo Zhao from Tippie College of Business at the University of Iowa. Renbo is an assistant professor there, and he obtained the PhD from MIT. He will talk about the Frank-Wolfe methods for minimizing log-homogeneous self-concordant barriers. Please, Renbo.
Thank you. Thank you so much, Johnson, for inviting me to give a talk here. Today, what I'm going to talk about is a part of my PhD thesis on this Frank-Wolfe methods for minimizing log-homogeneous self-concordant barriers. Uh, okay. So, okay. Yeah. So, right. So sorry for the problem here. So the problem that I intend to solve has this composite form, which is kind of common in the convex optimization setting. Okay? But the difference is that this function f, okay, typically has non-Lipschitz gradient properties. Okay? So this is the main technical challenge of this work. And in this work, we'll propose a class of functions. Actually, we'll identify a class of functions that Frank-Wolfe method actually will work well. So let me kind of walk you through this problem. Okay, so the function that we want to minimize is a capital Fx. Okay, it has two components. The first one is function f, as is composed with a linear operator a, and another function. The second function is h. Okay? And so a is a linear operator. Okay, it is not necessarily invertible, and typically, this A contains all the data. Right? So suppose, let's say you try to solve some problems from statistics, some machine learning, and all this data will typically encode this linear operator A. And so F is a theta log homogeneous self-concordant barrier. And we will, in the sequel, because this is really a long name, we'll say this theta LHSCB. So probably you have, if you have studied this interior point methods and especially prime dual interior point methods, okay, so this object is really at the core of this prime dual interior point methods. But here we are not talking about the interior point methods, but rather we want to say what we want to say is that so this type of functions actually naturally appears in a lot of applications where we naturally want to minimize these type of functions. Okay? And it is defined over some regular cone K. So for this type of functions, I will give a precise definition on the second slide, but just bear with me. Just let me to finish introducing every component of this optimization problem. And so H is a closed and convex function, and with a compact domain, which we denote by this calligraphic X. Okay? And for example, if H is the indicator function of some compact set, then that is one application. Okay? And that is one instance of this function H, but H can also be something else, for example, L1 norm or some very simple functions. So this H is not necessarily differentiable, but we assume that it is closed and convex, and it is relatively simple. And of course, we assume that the domain of F is non-empty. Here there is a typo here, so it should be non-empty. Meaning, under this assumption, so at least one minimizer exists, and we denote this minimizer. And we also define the optimal value as f star. And so it has many applications. I will give you some examples of the applications later on. Now, before I give you some applications, probably a lot of you are kind of curious or even confused about what is this log homogeneous self-concordant barriers. So let K to be a regular cone. Okay? So K is a closed convex pointed and non-plane interior. So sometimes we call it proper cone in the textbook by Boyd and Vandenberg. But here we call it a regular cone. Okay? And so F is a theta LHSAB on K with complexity parameter theta greater than or equal to 1. Okay? If F is 3 times differentiable and strictly convex on the interior of K and satisfies the following three properties. So the first one is the classical definition of self-concordant functions. So I believe all of you have learned in the first course of convex optimization. And the second one is that so the function has to blow up on the boundary, okay, which is the barrier property of the function. Okay? And the third one specifically explains why it is called logarithmic homogeneous. It means that suppose I fix any point in this interior K, and I scale it by T, then the function will behave like log along the ray of the cone. Right? Then probably I'll draw a picture. There's no markers. There any marker here? So it's fine. Probably I'll just use my hand to draw a picture here. Suppose let's say you have a cone here, and along the cone there are several rays, right? So suppose that if you fix one point and you try to scale this point right, along this ray. So along this ray, so the function will behave like log. So this explains this term here, this minus theta log t here. So that's why it's called log homogeneous. And how do we get this log homogeneous function? Suppose let's say we have a homogeneous. Suppose let's say we have a homogeneous function, positively homogeneous function with a degree theta, okay, and then we take minus log, then we get a log homogeneous function. That's how we typically get this log homogeneous function. And of course here, so there's a norm here, which is a local norm. Again, everyone has learned this in the interior point methods class. Right? So it is defined using the local hashing of the function f. So if you kind of confused or you find this definition is quite complicated, okay, there are two prototypical examples that I want to introduce. And in order to comprehend or understand this talk, you just need to know that these two functions belong to this class of functions. That's enough. Okay? So first one is a minus log of determinant. And it is defined on, it is actually a barrier function on the cone of positive semi-definite matrices. Okay? And this complexity parameter theta here is equal to k, okay? Because here is a k by k matrix. And the second one is the minus sum of all the logs. Okay? And so all these coefficients wj here is greater or equal to 1. Okay? And so this function is actually a barrier for the non-negative percent. Okay? And this complexity parameter theta is nothing but the sum of all the weights in front of the logs. So probably it's good time to pause here. Any questions about the definition? Yeah. So the take-home message is that all these two functions are log homogeneous self-concordant barriers. That's all. But in order to kind of develop our theory and also to kind of identify the broad class of problems that our Frank-Wolfe method can work, we want to leverage this concept. But in order for application-wise, these two functions will cover most of the applications. Right. So now let me introduce some applications. Right. So the first application is actually, this is my advisor Rob's favorite application. Okay. So this is a de-optimal design problem. Okay. So de-optimal design problem actually is a very old problem. Okay. It actually originates from the 1970s. It's a bunch of statisticians where they try to design experiments, okay, how to select the points to design a good experiment. Then this is how do they, this is one of the version to design a good experiment by the D criterion. So this is called de-optimal design problem. Okay. Actually here, it is really a convex relaxation or continuous relaxation of the de-optimal design problem, because the original problem is posed in the discrete setting. And so we try to, it's really a binary, all these variables are really binary, but here after convex relaxation, this is a form. And so this form is very simple. So we, as you can see here, the optimization variable is a vector, actually is a probability vector in the sense that it lies in the unit simplex. So all the components are greater or equal to 0, and the sum is 1. Right? So this is, you can interpret as a probability vector or any point in the unit simplex. And then, the objective function is basically a minus log determinant, okay, composed with a linear transformation of this PI. So this class of this de-optimal design problem nicely fits into the problem class that we introduced at the beginning. So all this data here, so we have so the problem data is very simple. It basically just so it just endpoints in the n-dimensional space. Okay? So all these AIs, okay, they are just endpoints, okay, the set of endpoints in the n-dimensional space. And in order for this problem to be valid, so the linear span must be equal to Rn. Otherwise, the problem is ill-posed. And it has included a lot of applications, not only the optimal experimental design, the statistics, But in computational geometry, this actually arises at the dual problem of the very famous minimum volume enclosing ellipsoid problem, okay, which has been studied for many years, okay, and still it is a hot. Still, some people from the theoretical computer science community are still studying this nowadays. Okay? And in order to solve this problem, typically people will look at this dual and solve this optimal design problem instead. And what it really motivates the study of this is actually a famous paper by Kachin in 1996. So in Kachin in 1996, he proposed a barycentric coordinate descent method, okay, with the exact line search. Okay. So by that time, Kachin was not aware of any Frank-Wolfe literature, and he basically just proposed this method. Okay. Actually, this method was initially proposed by Fedorov in the 1970s. But the innovation of Kachin is that he gives the first complexity analysis of this method, which is very innovative. Okay? But here, if we really view his method from the Frank-Wolfe perspective, it is nothing but Frank-Wolfe with exact line search. Okay? And this method actually works very well in theory and practice, because each time the computation is very cheap. Okay? It is not some kind of interior point methods where each time, so we need to solve some expensive Newton equations. And the problem, and Kachin's method is very cheap. It's actually a first order method. Okay? But the problem is, the success of this method cannot be explained by the traditional Frank-Wolfe theory, because this log determinant function, or this minus log that function, okay, is very troublesome in the sense that it does not have Lipschitz gradient. Right? And if you have learned this first order method, this very basic theory of first order method, okay, so the lack of non-Lipschitz gradient basically destroys 99% of the theory. So, and the question that my advisor have been thinking for many years is that how do we really demystify Kachin's method, in the sense that his method, his analysis is so beautiful, it's so clean. Okay? But on the other hand, this function is very problematic in the viewpoint of traditional first order method. How do we explain the success of his analysis, and how do we explain the success of this Frank-Wolfe method? And that basically motivates the work of this current work. Okay. And later on, I'll show that, okay, so there's nothing different, nothing special about this log depth function. Okay. It is really the log-homogeneous self-concordant barrier property that explains the success of the entire method. In other words, as long as we have a log-homogeneous self-concordant barrier, okay, then any Frank-Wolfe method will work for this problem. Okay. And we essentially can recover Kachin's analysis on this very special case. And so his analysis actually mentioned that is n squared over epsilon time iterations. So n is a dimension of this problem data. Actually, if you look at carefully, n is also the complexity parameter of this log depth function, because the log depth function, okay, is defined on an n by n positive semi-definite matrices, okay, on a set of cone of n by n positive semi-definite matrices. Right, so this n here is really the complexity parameter of this log depth function. So that kind of shows you the analysis, so the connection between Kachin's analysis to the broader class of barriers, log-homogeneous barriers. Right. So as I mentioned, so the success of this method has been an outlier, mysterious outlier for more than 20 years, and now, and the part of the motivation of this work is to demystify this method. Okay? And another contribution is that we not only demystify Kachin's method, actually we propose a more flexible Frank-Wolfe method, in the sense that each time we do not need an exact line search of this Frank-Wolfe method, because for some problems the exact line search is simply not feasible. And actually we propose a method that can, at each step, we can exactly compute the step size. It's not exact line search. We have an explicit formula to compute the step size, right? So the method becomes completely implementable, but we can retain the theoretical guarantees of the Frank-Wolfe method with exact line search. That is another contribution of this work. Okay. So probably I will talk about a lot about the theory. So probably I'll show you some images. Just keep you online. Okay. So here we have this true image X. So the application is really persona image denoising with TV regularization. So now we have the true image, which is X, and after some noise, after some noising process, for example, we can blur this image, okay, which is a linear transformation. We use convolution operator to blur this image, and we can add some Poisson noise. Okay, now we have a noisy image Y. And so here, so this we use each image can be encoded as this n by n matrix. Okay? And so for each entry of the matrix, it represents 1 pixel of the image. Right? And so this n is a 2D discrete convolutional operator. Okay? We assume that we know this linear operator because in a lot of imaging applications, actually people do know this linear operator. And based on the knowledge of the linear operator, we actually want to solve this problem. Solve the following problem, okay, in order to recover the clean image. Okay. And as you can, as we will explain later on, okay, probably just now, probably right now, this function, this type of application fits nicely with the problem class that we identified at the beginning, in the sense that here the first 2 terms are the log-homogeneous barriers. Okay. So the first one is a log-homogeneous barrier. Okay. So the second one, so the second and third term actually all goes into this function h, which is a relatively simple, closed and convex function. And so the constraint set is basically a box.
And then we can also include the second term, right?
Oh, so for the second term, if you include that, that's not a barrier. That's a self-concordant function, but that's not a barrier.
Oh, not a barrier.
Yeah, because so if we have a leader term here, that destroys the barrier problem. Yeah, that's a good question. Yeah. So for the TV regularization here, it just basically takes these adjacent pixels. Suppose let's say you have an image and then you have a lot of pixels, right? And basically the TV function, it kind of takes the adjacent pixels and then calculates the difference of these 2 pixels and put absolute values. So basically it's that, it takes all the adjacent absolute differences of all the pixels and then sums them up. Okay? And this TV regularization, this TV function, total variation function, okay, is very famous function to encourage the smoothness of the recovered images. Okay? So it is quite frequently used in the image processing communities here. And here, for the purpose of our exposition, we actually already vectorized this image to a vector, which we are allowed to do that, and it doesn't lose generality.
What is the little e?
Oh, the little e over here, yeah, that's a good question. Little e is the vector 1, the vector of all ones. Okay, so sometimes we use both this 1 to denote this vector. Okay, yeah, that's a good question. Yeah. So, and it also has several more applications. For example, it is used in analyzing the social networks in the sense that, so the learning of the multivariate Hawkes process problems can also fit. It's also one application of our problem. Okay? And also so in medical imaging, there's something called positional emission tomography, and that problem also fits into our template. And there are actually many more. In quantum physics, there's something called quantum state tomography, and this one is actually so the optimization variable is a positive semi-definite formation matrices, because because this type of matrix really encodes the quantum state. And also in computational geometry, we want to compute the analytic center of the polytope. This is also one application. Okay? So this problem class kind of includes many applications. Okay? But due to time constraint, we cannot just introduce everything. Okay? And now let us introduce our method. We have talked about applications, and we have talked about the definitions of the log-homogeneous barriers, but really, what is our method? Okay? So the method here, just to remind you about this is the problem we try to minimize. Okay? So our method is really simple. Okay? It falls into this Frank-Wolfe type of framework, but the true innovation is the step size. How do we judiciously choose the step size so to make the Frank-Wolfe method to work for this type of problems that does not fit into the classical literature. So for the first one is that we compute vertex. We really compute a V here, right? So that is the minimization. That is the argument, or really the optimal solution of this subproblem. This is a simple subproblem, which we call this a linear subproblem. Okay? And here, if So here really what we try to do here is to propose a generalized Frank-Wolfe method in the sense that this H, if it is the indicator function of some polytope, for example, then this is a classical Frank-Wolfe method. But here, if we allow H to be not just the indicator function, but some very simple function, for example, L1 norm, then this linear subproblem can also be very easily solved. And then this somehow makes the Frank-Wolfe method slightly more general. But if you find this is a little bit hard to understand, just think about this H as some indicator function. Then really what we are trying to do is to minimize a linear function over some convex and convex set. For example, a polytope. If it's a polytope, this is LP, right? So for LP, we can use some LP solvers to solve this problem. And for a lot of structured LP, we can zero some special solvers for solve this problem. And after getting this point, and then we can compute the Frank-Wolfe gap here. After computing the Frank-Wolfe gap, then we compute really the local norm of this one. So this is the VK minus XK, which is the difference between these 2 points. So XK is a current iterate. This VK is a point that we compute. And after getting their difference, we do a linear transformation, and then we evaluate the norm of this object at the current iterate xk. And the local norm, again, is defined with respect to f, which is a log variable, so that the hashing is positive definite, so we have a norm. And so this is a local norm that we compute. And after that, we compute the step size. So step size looks at something like this. If you are a little bit familiar with Frank-Wolfe, typically we have this 2 over k plus 2 step size, which is kind of non-adaptive, but it works well for Lipschitz gradient functions. But now, because we do not have this Lipschitz gradient property, we can now use this so-called open loop or non-adaptive step sizes. We have to adapt to the local geometry or local curvature of the function. And that's why we have this step size here. And as you can see here, so the step size makes of a lot of information at this xk. So it involves this local distance here, and it also involves the Frank-Wolfe gap here. Okay. And then we have the step size. And after computing the step size, the algorithm proceeds by finding the next iterate by doing something like this. So this VK minus XK is really the search direction. So basically we have some XK here, and then we have a VK we compute. And then basically VK minus XK is the search direction here. And we multiply this direction using the alpha k, which is the step size, then we get the next iterate. So structurally, this is very simple. Okay? But probably what is non-trivial is this step. How do we get the step size? And that is non-trivial. That is a non-trivial step. And how do we, of course, how do we analyze the performance of this one? That's also not trivial. And that's basically our algorithm. It's pretty simple. Okay? And so let us make some remarks here. So probably if some of you might have this question, computing this local norm involves hashing, and then this can incur high computational cost. Okay. But actually, for a lot of applications in practice, this local distance, because the function has some special structures, okay, so the local distance can be computed in O(n) time. So n is a dimension of the problem instead of O(n) squared time. The reason is because typically the hashing admits some low-rank factorization form, and the hashing has this factorization form is not only is not because we are explicitly doing some low-rank factorization, but it's just because the structure of this problem naturally gives us this factorized hashing. And by using this factorized form of this hashing, so this local distance can be computed in O(n) time, which is linear in dimension, but not quadratic in dimension. So here, computing, although we are using the hashing information at this step, but here in terms of computational cost, this is really more similar to the first order method than any second order method, okay? Because this step can be typically computed in time that is linear in dimension. And another thing I should mention is that so the Frank-Wolfe gap actually is upper bound for this objective gap. And typically, this is well known in the Frank-Wolfe literature, and this is all because the convexity of the problem. This is very simple, but I should mention this because a lot of times we are not only interested in the convergence or really in the complexity of this delta K here. We're also interested in the complexity to obtain a small GK or the Frank-Wolfe gap, because a lot of times we use this Frank-Wolfe gap to terminate this algorithm. Because in practice, we never know what delta K is, but we do know GK. And one of the beauty of this Frank-Wolfe algorithm is that it has this very natural byproduct in the algorithm that can allow us to terminate this algorithm very easily. That is this fact. And also, probably one mysterious fact is that how do we get this step size? Well, actually, we get this step size by a curvature condition of this self-concordant function. If f is self-concordant, then actually we will have this curvature condition. You can find this formula from Yuri Nesterov's textbook. So there's no rocket science here. But if we use this curvature condition, which is specific to this self-concordant function, then after you differentiate and you do all the math, you will recover this step size that we have here. So this is, and this, as you can see here, this curvature function is actually very different from the Lipschitz, the so-called descent lemma, which is for the Lipschitz gradient function, and it is very different from that one. And specifically, it involves the decay, which is a local distance here. So everything about self-concordant function is actually measured locally. That is one of the most useful property of the self-concordant function. And for some applications, for example, the de-optimally design problem, as already discovered by Kachin and some very famous statisticians, the step size can indeed be efficiently computed by exact line search. But here, because not all applications can have these nice structures, so that's why we propose this so-called adaptive step size, so that our algorithm can be applied to every application that we encounter in real life. So now I will show you the algorithms. So before I show you any computational guarantees, are there any questions about this algorithm? All right. So now let me show you the guarantees here. Okay. So in order to define the guarantees, it involves one quantity, which is RH. So RH is really the the variation of this function h on its domain. Right? So basically, we just take 2 points on the domain, and we can compute the largest absolute difference. Well, if you think about this h as an indicator function, this one is simply 0, because indicator function on the domain, right? So it is 0, and then this RH becomes 0. But here, because we allow h to be a non-indicator function, for example, again, an L1 norm or some kind of L2 norm, okay? So this RH can be non-zero, but it is the variation of h on its domain. Okay? And also, we have this delta 0 to denote the initial optimality gap. Okay? And here is our theorem. So the first theorem is that the iteration complexity of this to obtain a theta objective gap. So the theta objective gap can be obtained with k epsilon iterations, okay? And this k epsilon can be bounded as something like this. And as you can see here, we have 2 terms here, and the first term is really the overhead. It does not depend on epsilon. Probably you have already noticed. Only the second term depends on epsilon. Right? The first term does not depend on epsilon. Okay? So if we kind of ignore the first term, which is the overhead, just let me try to hand wave a little bit here and try to just focus on the dependence on epsilon. It is really theta plus RH squared over epsilon, because typically this epsilon is smaller than delta 0, so we can just ignore this part. Then it is basically theta plus RH squared over epsilon. And for this if this h is an indicator function, we know that RH is 0, right? Then we can get rid of this RH term. So essentially, for this special case where h is an indicator function, we have theta squared over epsilon. That is the complexity, essentially. But if we recall what is the Kachin's complexity for the de-optimal design problem, that is n squared over epsilon. So essentially, we have recovered Kachin's complexity results. And actually, we have recovered, and we have actually have significantly generalized his result to a wide class of problems. Any questions for this one? Okay. And the second one, okay, is the iteration complexity to obtain an epsilon Frank-Wolfe gap. So as I mentioned just now, so in the Frank-Wolfe literature, we not only care about this optimality gap, we also care about this Frank-Wolfe gap. The reason is because Frank-Wolfe gap is a very nice criterion for us to terminate this algorithm. So that's why we can also give a guarantee for to obtain epsilon Frank-Wolfe gap. And as you can see here, basically they are the same. Right? So probably some constant is different, but basically in terms of otherwise, right, this is really the same as obtain that epsilon optimality gap. So basically essentially with the same complexity, we can get both an epsilon optimality gap and epsilon Frank-Wolfe gap. And one thing also I should also mention here is that this for this expression, it only involves 3 objects, as you can see here. Right? It only involves theta, which is the complexity parameter of the Berry. It involves the delta 0, which is the initial optimality gap, which makes sense because the higher the initial optimality gap, the longer iteration that we can get an epsilon optimality gap, which makes sense. And also it depends on this RH, which is a variation function of H. And a lot of times it's just 0 if H is an indicator function. So it does not depend. So, and all of these quantities, okay, and for example, so theta can be known beforehand because a lot of times once we know this log homogeneous barrier, we immediately know theta. A lot of times we know theta just beforehand. So it only involves these 3 quantities. And for all of these for many applications, actually, all the 3 quantities can be easily estimated. And this is in contrast with some potential approaches of taking sublevel set and calculating the smoothness parameters of the sublevel set. And typically if we try to use those approaches, first of all, those approaches might not work well for these problems because this problem got some special structures here. And even if we use those approaches, those quantities can be relatively hard to estimate. But if we go analysis by this route, okay, so all the 3 quantities are easily estimated. So finally, so this is the first part of the talk. So for the first part, I'll show you some numerical experiments. So for the numerical experiments, let me show you again the image deburring example with TV regularization. So as I mentioned just now, so here we have the first term is the differentiable part, which is the sum of those minus logs, and the second part is the TV function. So here, so if we notice that this TV function is actually polyhedral, it's a polyhedral function because it is sum of all these absolute differences between adjacent pixels. So naturally, it is a polyhedral function. Okay. And to solve this subproblem, which is shown here, it is a relatively simple LP because this subproblem can be solved using a specialized network LP solver. Because if we kind of think about this image as a network, well, it's actually a very simple network. So each time, so there between 2 pixels, there's a link. So there's a link between one pixel and the pixel above it. And then we calculate the difference between these 2 adjacent pixels, and then we put all the absolute differences into the TV function. So this subproblem actually can be, of course, it can be reformulated as an LP, but it's not some kind of arbitrary LP because the special structure of the TV function, it is actually a network LP. And for network LP, there are a lot of efficient methods to solve this problem. So the point is that this problem can be solved using a relatively simple LP solver, for example, Groby. Any questions about this one? Okay. So we have 2 versions of our algorithms. The first one is this adaptive step size, and the other one is exact line search. So for these problems, there actually exists some exact line search procedure. So we actually discovered exact line search procedure for this Frank-Wolfe algorithm. Okay. And so we tested both versions. One is the adaptive step size, the other is exact line search on this Sharp-Logan phantom image, which is the image that I showed at the very beginning. And this is really a canonical test image for the medical imaging because it nicely simulates the structure of the brain. So as you can see here, this is the true image. This is the noisy image after blurring and all this ozone noise. And let me show you what is the result recovered by the two versions of our algorithm. Actually, as you can see here, this Frank-Wolfe with exact line search actually gets you a slightly better image compared to the Frank-Wolfe with adaptive step size. And this is kind of intuitive because once we use this Frank-Wolfe with exact line search, we're really pushing the step size to its optimal at each point. So each time the Frank-Wolfe with exact line search kind of makes better progress compared to adaptive step size. And because it makes it, and within the same amount of time, because this Frank-Wolfe with exact line search, it makes better progress at each iteration. So naturally, at the end of this time period, it will give us an image that is slightly better compared to this Frank-Wolfe with adaptive step size. And if you cannot see the difference, let me show you the plot. So as you can see here for the plot, this is a decrease of this objective gap. And as you see here, this Frank-Wolfe, the blue line encodes the Frank-Wolfe with exact line search. It certainly makes a better progress compared to the Frank-Wolfe with adaptive step size. But as you can see here, if we kind of allow more time for the numerical experiments, then eventually there's a tendency that Frank-Wolfe with adaptive step size will catch up. But we stop at this 10 to the power 4 seconds. I think it's really 10,000 seconds. And as you can see here from this plot, the Frank-Wolfe with exact line search makes better progress. And this is versus time, this is versus iterations, which kind of makes sense. But in terms of theory, yeah, so I should mention that in terms of theory, we get all the theory from the adaptive step size. And then really in terms of theory, we cannot really explain the difference here. So our theory applies to adaptive step size, which naturally applies to the exact line search. But the benefit of exact line search in practice is an open problem for exploration from the theory viewpoint. Any questions? So probably let's see how much time do I have about this? Okay, so
we finished at 12:05 because we started at 11:05.
oh, okay. So I still have about 20 minutes. Okay.
20 minutes.
Okay, thank you. Right. So here, so second part of the talk is really a follow-up of the first one in the sense that I was trying to develop this Frank-Wolfe method with a V-step for the same class of problems. Actually, slightly more restricted class of problems that I showed you at the beginning. Probably I will not go through all the slides of the second part of the work because it is really a follow-up work. There were some nice ideas in this, but it is slightly more complicated. So I will try to convey the main ideas, and I will leave the technical details, probably offline. And again, so the motivating example for the second part of work is still our old friend, which is the optimal design. Actually, just now I've shown you, this Cartesian barycentric coordinate descent algorithm works very well. But let me now tell you, it is not the fastest algorithm for solving this problem. Actually, the fastest algorithm, right? So in terms of theory and practice, for solving this algorithm is actually algorithm proposed by a famous statistician called Atwood in 1970s. And it is basically the Frank-Wolfe method composed plus the V steps. So this algorithm has been proposed by 1970s. It is really a variant of the Cartesian or really Federer's vanilla Frank-Wolfe algorithm, but just with the addition of V steps. But the analysis is kind of is still an open problem till now. Now, let me kind of do a quick recap of the optimal design problem. Now we try to minimize the minus log that function. Okay, so we have endpoints, which is the problem data, and it has applications, blah blah blah. Okay, so what is the algorithm proposed by Atwood in 1973? Okay, so this algorithm structurally, it is a Frank-Wolfe algorithm, but in each time, okay, it actually computes 2 points here. So the first one is that it takes the gradient of this function. It computes the index corresponding to the minimum entry of the gradient. And then it computes a Frank-Wolfe gap in the form of this. And the second step, which is really an extra component compared to the vanilla Frank-Wolfe algorithm, is that it also takes the same gradient. It on the support of the current iterate xk. Remember that this x lives in the unit simplex. So on the support of the current xk, it computes the index with a maximum entry of the gradient. So now we have really, instead of having one index ik, right, which is the vanilla Frank-Wolfe algorithm, and now we have two indices. Okay? And for this extra index, which is a gk, we can also compute another quantity. Okay? This is not a Frank-Wolfe gap, but this is another quantity. Okay? And then we compare these two quantities. Remember, this gk is a Frank-Wolfe gap, and this one is another positive quantity. And if gk is greater than this gq k, right, then we take the direction given by the vanilla Frank-Wolfe gap. And in this case, it got nothing to, it is exactly the same as Frank-Wolfe algorithm for this particular iteration. But if this Frank-Wolfe gap here is smaller than gq k, then we take another step given by this jk. And this is called a weight step. So each time, instead of comparing, essentially what this algorithm is doing is that, so the vanilla Frank-Wolfe algorithm, it computes one such direction. But here, since this is a weight step algorithm, okay, it computes two directions. Instead of one direction, it computes two directions. Okay? And it compares these two directions based on the two quantities associated with each point. And by comparing these two quantities, we decide which direction to take. Right? So this is the philosophy of this weight step Frank-Wolfe algorithm. And after computing this direction, then we compute the step size, then we just take the next step. That's all. So this algorithm actually, when Edward did his numerical experiments back in 1973, well, back then it was definitely very preliminary example, numerical experiments, but he actually found this algorithm works much better compared to the vanilla Frank-Wolfe algorithm. Because why is that? Right? Because at each iteration, the additional calculation of this step poses almost no additional computational burden. Right? So we are still taking the same gradient, we just compute the maximum entry, and then we just do a simple calculation here. It just creates almost no extra computational burden. But as I will show you in this talk, this algorithm actually has global linear convergence. Like if you recall, the Frank-Wolfe here is just global sublinear convergence, 1/k convergence rate. But for this algorithm, it actually has global linear convergence. That's why numerically, it was much better compared to the vanilla Frank-Wolfe algorithm. Because at each iteration, these two algorithms have roughly the same computational burden. But this algorithm, in terms of conversion rate, is much faster compared to Paschin's algorithm. That's why it has better numerical performance here. And so this algorithm, okay, was actually discovered by many people. So actually, this algorithm structurally coincides with the Frank-Wolfe algorithm with a weight step developed by Philip Wolff in 1970. And actually, Mike Todd and during the 2025 and 28, that period, okay, actually he intensively investigated the minimum volume enclosing ellipsoid problem, where the dual problem is really the optimal design problem. So he has one paper, has really several papers of this particular method. Okay? And actually, in one of his papers with Alper Ildarian, they actually rediscovered this method. So that's why, for this reason, for historical reason, we'll refer to this method as WATY method. So each letter actually encodes one discoverer of this method. And so let me show you some numerical performance of this method. Okay? As you can see here, there actually in the literature there were several first-order methods able to solve this problem. So this is the focus of the second part of the talk, which is the Atwood algorithm or WATY method. Okay? As you can see here, both ones. Okay? So these are really two versions of this algorithm. Actually, they have this linear convergence. So this is really a log linear plot. Right? So this is a log linear plot, and we observe the straight line. This indicates global linear convergence. But for some other methods, for example, this is the method that I talked about just now, okay, in the first part of this talk. It has this 1/k sublinear convergence. Okay? And also there are some other methods, for example, the relatively smooth gradient method, okay, proposed by Nasrov and my advisor Rolf Ron. Okay? And some other people, okay, they also have this 1/k convergence rate. And also there is some specialized method for this problem called the multiplicative gradient method. It also has sublinear, right? But this method, this away-step Frank-Wolfe method, has this striking global linear convergence rate. And in terms of the computational time, it actually significantly beats all the other methods. And this is not only this is not the end of the story. Actually, what is more surprising is that, or what is more encouraging is that, suppose let's say we want to obtain a sparse solution, right? Because a lot of times we desire a sparse solution, and because for this de-optimal design problem, okay, the variable x really lives in the unit simplex, so it is very natural to talk about the sparsity of the iterates. And for all of these other methods, okay, if you look at the number of non-zero elements of the sequence of iterates generated by this method, well, most of the methods, they just, fully dense. They generate the iterate that proceeds in the relative interior of the simplex method, of the unit simplex. Hence, the sparsity, basically, the iterate they generate is fully dense. The number of non-zeros remains at the initial one, which is 2000. But as you can see, this away-step method, it drastically reduced the number of non-zero points, non-zero iterates, to around 800. And this, in terms of sparsity, it also has much more superior performance compared to some other first-order methods. So this kind of, because of all this superior numerical performance, this makes study of this away-step Frank-Wolfe method worthwhile. Good. Are there any questions about the numericals? Right. So there's one example. Okay, so my colleague actually with his advisor, with his collaborator is actually intensively studied this algorithm, okay, around 2010, around that period. And in one of the papers, they actually show this method has local linear convergence. Okay, but the global linear convergence remains open. Because just now, when we do these numerical experiments, we indeed observe this global linear convergence phenomenon, but they are only able to show this local linear convergence. But in this work, I'm going to show you that this class of methods, this method, not only on the optimal design problem, but on a broad class of problems, achieves global linear convergence. So in particular, when it specializes to the optimal design problem, it settles the open question in this paper. So there were two structural difficulties of this method. So the first one is that M does not have Lipschitz gradient on a constant set. And the second one is that F is degenerate on the feasible region. Is because the linear operator actually is non-invertible. So the hashing is actually not positive definite. So that is basically two structural difficulties of this problem. Probably due to the time constraint, so let me quickly show you what is the problem that my method can apply, okay, and what is the computational guarantees. So as I mentioned at the beginning of the second part of the talk, so this problem that I am able to solve is actually more restricted compared to the example of the class of problems I showed you at the beginning.